We're on part three of the course, continuing on part three of the course, and we're looking at work as a method of heat transfer and the first law of thermodynamics, which essentially ties work, energy, and heat together. So work is defined as the energy transfer associated with the force acting through a distance. So if you can imagine pushing a box across a room, it's the force required to push that box multiplied by the distance it's displaced will give us the work done. And the displacement is meters, the force is in newtons. So 1 Newton meter equals 1 joule, and that's the SI unit for work, which is the same as heat and the same for energy. Interesting aspect about work is that when you stop pushing that box across the room, work no longer exists. It's a transient property, so you can't store it or harness it for later use. Force and displacement are vector quantities, which means they have a magnitude and a direction. So when the force is acting in the same direction as the displacement, it's simply a matter of multiplying the two of them together. But when the force is, let's say, acting at an angle to the displacement, the maths is slightly different. So here we have an example of a skier being pulled up a slope by a ski toe. And the ski toe is acting at an angle of 30 degrees to the slope. So what we need to do is we need to resolve the force into its horizontal and vertical component. The vertical component's not doing any of the work. All the work is being done by the horizontal component. So we multiply the horizontal component by the displacement. So you've got S multiplied by F cosine theta, and then you have the work done during that process. The work done per unit time is called power. It's denoted by W dot, and it's in kilojoules per second or kilowatts. Now, work in thermodynamic systems can be categorized into two forms, mechanical forms of work and non-mechanical forms of work. So example of mechanical forms are piston, shaft, spring, elastic bar, surface tension, and then examples of non-mechanical are electrical work and magnetic work. So we look at some of these and show how they can be calculated. So piston work is the work associated with the compressing or expansion of a gas in a piston cylinder device. So we heat up the gas here and the piston, the gas expands and the piston moves and does some kind of work for us. So we see them in car engines where a number of them acting in parallel are each distributing a certain amount of work to the crankshaft, and that linear motion is being moved into rotary motion to move the car forward. And we'll see them in compressors, devices that take in a gas at a low pressure and expel it out at a higher pressure. So compressors, for example, would be used in refrigeration systems to create that important pressure difference across the evaporator and condenser. And then they would be used in hydraulic systems, pneumatic systems, and reciprocating pumps, for example, as well. Piston work is something that we will elaborate on, and I think it's part 6 of the course. So for the moment, we'll leave that there. Shaft work refers to the mechanical work transmitted by a rotating shaft in a system. And where we would see shaft work would be, for example, when we boil up the water, turn it into high temperature steam or superheated steam, the energy in the steam rotates the turbine. And as the shaft rotates, that shaft work coming out. It will be coupled to a generator, and that shaft work would ultimately be turned into electrical work. We have a pump down here, so when we switch on the pump, electrical energy is being turned into mechanical shaft work in the shaft. We have an impeller on the shaft, and it becomes a pump, and it takes the liquid condensed water and feeds back to the boiler again. So we've an amount of shaft work coming out of the heat engine, which is the power plant, and an amount of work going in as well. Steam engines on boats, for example, steam would turn the turbine once again, and the turbine blades are connected to a shaft, and at the end of that shaft is an impeller, and as that impeller rotates, it drives the boat through the water. We'll see shaft work in the in a car, for example, in the forms of the crankshaft and the drive shaft as well. So how do we calculate shaft work? Shaft work, once again, is the energy transmitted by a rotating shaft, and it's force by displacement. So the tangential force we see here acting on a shaft, that there's a torque. You might come across torque in Newton meters as a measure of the rotational force F, that tangential force, applied to an object acting through a moment or. So the torque is that tangential force there multiplied by that moment or the radius or about which it turns. So we can transpose this equation here to get the tangential force on its own. We can put torque divided by R in our work equation for force. Now, the distance that this point that the tangential force is acting upon, the distance that makes in one revolution is 2 pi r, and then the absolute distance it makes is 2 pi r n, and that's n being the absolute number of revolutions. So we put 2 pi r n into the equation for displacement. We notice that the r's cancel, and we're left with torque by 2 pi n for the shaft work. Now, seldom do we know the absolute number of revolutions that a shaft makes. But what we do know quite often is, and it's easy to obtain, is the revolutions per minute or the revolutions per second. If we have the revolutions per second, we have the rate of doing work, the work done per unit time. And the work done per unit time is what we call the power. So we've the power here, W dot, and the SH to denote it's for the shaft. And it's 2 pi n dot T, where n dot is the amount of revolutions per second. Now, there's another relationship in there, and it's 2 pi n dot is actually the angular velocity in radians per second. So 1 radian, just to mention, is the angle subtended at the center of a circle by an arc that's equal in length to 1 radius. So simple example there, determine the power transmitted through the shaft of a car when the torque applied is 200 Newton meters and the shaft rotates at a rate of 4,000 RPM. So we'll change the 2,000 RPM to revs per second. So divide by 60, so it's 2 pi n dot by torque, and we get 83.786 kilowatts. Okay, spring work. Spring work is the energy associated with the changing the length of a spring. So we put a force acting on a spring, a weight on that spring. The differential amount of work here is equal to the force by the distance displaced, dx. Now, for real springs, if we want to know the total amount of work being done through the extension of a spring, we need to understand the particular relationship between force and displacement for that particular spring. And that's defined by what we call Hooke's law. And Hooke's law tells us that the force is proportional to the displacement x by the spring constant k. So the force equals the spring constant k in newtons per meter by the displacement. The spring constant is specific to different types of springs, taking into consideration the geometry, the size, for example, the length, the coil diameter, the thickness of each coil, or the coil itself, the material type as well, and the nature of the spring, whether it's a compressive spring or a tensile spring or even a torsional spring. All of that's taken into consideration to define the spring constant, which we would need to factor in when we're trying to understand the force by displacement for a particular spring. Now, if we were to plot force against displacement for a linear spring, we would get a straight line plot like this. And the slope of that line is the spring constant K. And the area under this line during that extension is the work done during the extension of that spring. So we can express the force on this axis here in terms of the spring constant and the displacement. So the work then is a half times kx by x, which gives us a half times kx squared. So the work done in extending a particular spring of a particular spring constant is a half times the spring constant by the displacement squared. And where we see spring work coming into play would be in the trigger mechanisms for firearms, for example, in the valves for an engine to open and close the valves, and then in suspension systems to be able to determine whether these devices, whether the suspension system will work or a trigger mechanism will work for us. Simple example here, this will be a pneumatic or a hydraulic system. It could be a materials handling system. It could even be a safety interlock or something like that. And calculate the work done by a spring with a K value of 100 newtons per meter in returning a spring at distance of 120 millimeters. So we just changed that 120 to meters, so get 0.12 meters, square it and multiply it by the spring constant and divide by 2. So 0.72 joules in returning this piston back to its original position. Electric bar work is the work associated with the deformation of solids under the influence of compressive or tensile stress. So we're put a load on this this solid bar here. The distance that it's displaced, we can get the work done during the displacement. And this is kind of this would relate to maybe structural elements. We want to know whether bridges, for example, will take a traffic load, withstand seismic activities, or be able to withstand strong winds as well. What we do, we express the force in terms of the normal stress here and the area over which it acts, and then the distance that it's displaced. So a bar of 1 meter is subjected to an axial tensile force leading to a normal stress along its length. The bar has a cross-sectional area of 0.001 meters squared, and it's made of a material with a Young's modulus of 2000 gigapascals. The force increases the length of the bar by 0.005 meters. We're asked to find the work done on the bar by this stress. So we know Young's modulus equals stress over strain. So we transpose that to get the normal stress on its own. And the strain itself is the change in length over the original length. And so we get that value also. So from that, we can calculate from Young's modulus and the strain, we can calculate the normal stress. And we can put that into our equation over here, our work equation. And then we have our area over which it's acting. And we have the change in length. And in this case, the work done on the elastic bar by the normal stress is 5,000 joules or 5 kilojoules. So surface tension work refers to the energy required to increase the surface area of a liquid. This concept is critical in understanding phenomena like droplet formations, capillary action, and bubble formation. Surface tension acts as a restoring force aiming to minimize surface area, and it plays a significant role in various physical and industrial processes where liquids are involved. So it could be pharmaceutical industries developing detergents and soaps and things. It could be the drinks industry and so on. So simple example here, soap film suspended on a wire frame. So what we have here is we've got a wire frame. One side of it's movable, and then we have this soapy film. And we want to know what the work done is on actually stretching that film of soapy liquid. So what we do is we we have the surface tension, which will be given, and then the change in area. So the change in area is the dx value down here by the breadth, but in this case, there's two sides exposed. So basically two surfaces. So we multiply the area by 2 in this particular case. So here's an example using bubbles. A spherical ammonia bubble rises in liquid ammonia. Its diameter changes from 10 millimeters to 30 millimeters. Calculate the amount of work required to increase the size of the bubble if the surface tension of ammonia is 0.02 newtons per meter. So we have our surface tension. What we need is the change in area. So the area of a sphere is 4 pi r squared. And we have our two diameters, so just change them to radiuses in meters. And we work out the change in the area here. Add that in with our normal stress. And we get 5.03 by 10 to the power minus 5 kilojoules. That's the work in changing the size of that bubble to the large size. Electrical work is the work done by an electrical current, and it's given by the voltage, by the current, by the time. So voltage is in joules, and the current, the I is in the V, sorry, is the voltage, I is the current, and T is the time in seconds. Now we want the power, it's the rate of doing work measured in watts. So we take that power here and divide it by time. So the times cancel, and we're just left with voltage by current in watts. Now power can also be expressed in terms of resistance, the current squared by the resistance, or the voltage squared divided by the resistance, according to the Ohm's law relationship that tells us voltage equals current by resistance. So an example of that, a piston cylinder device initially contains 0.5 meters cubed of nitrogen gas. An electric heater within the device is turned on and is allowed to pass the current of 2 amps for 5 minutes from a 120 volt source. Determine the electrical work done on the nitrogen. So the electrical work is the voltage by the current by the time. So we have that 120 volts by 2 amps, and we have the minutes multiplied, 5 minutes multiplied by 60 to get it into seconds, and it works out ultimately as 72 kilojoules. But another example, determine the power required to accelerate a 900 kilogram car from rest to a velocity of 80 kilometers an hour in 20 seconds on a level road. So the work required to accelerate a body is the change in the kinetic energy of the body. So let's first of all change the 80 kilometers an hour to meters per second. So we multiply by 1,000 and divide by 3,600. And what we want is we want a change in kinetic energy. So we get the half m, and it's the change in velocity there. And but the initial velocity is 0. So it's a half m v squared with the v being the final velocity. And we end up with a work of 222 kilojoules. If we divide that by time, we get the work done per unit time, which is the power, and that's 11.4 kilowatts. So there's a sign convention for work and for heat. So let's look at work for the moment. Energy may be transferred in and out of the control volume by work transfer. The sign convention for work transfer is important, but it may vary between different thermodynamic books. So the classical physics sign convention for work is given below, and its significance we made clear when we perform analysis. Closed systems of part 6. So the sign convention can differ from different books. Generally, there's one approach taken for thermodynamics in physics, and there's another approach taken for thermodynamics in chemistry. But even within thermodynamics itself, the sign conventions can be switched. So the one that we'll accept is that when work is done by a system on the surroundings, it's positive. So if we're doing work on the surroundings, delivering work, let's say to a crankshaft, it's rotating, that's during an expansion process, we will regard that as being positive. Now, when work is done on the system by the surroundings, when we're compressing the gas, we're taking energy from the environment to do that. So we'll regard that as negative. And when it comes to heat transfer to a system is normally taken to be positive with respect to the system. So the one way of thinking about this is if you're applying heat to the gas is increasing in temperature. So we'll regard that as positive. But when we are taking energy out of the gas, when it's cooling down, the temperature is decreasing. So we'll regard heat in that case as being negative. So now what we're going to do is move on to the first law of thermodynamics and see how it applies to a thermodynamic system. So the first law of thermodynamics states that energy can neither be created nor destroyed during a process, only change form. So for example, the total energy, we express it then mathematically, total energy entering the system minus the total energy leaving the system equals the change in energy of the system. So we're accounting for the energy somewhere. It's either coming in or going out, or it's still in the system. If we look at the right-hand side of that equation, change in the energy of the system, that can occur three ways. It can occur in the change of internal energy, the change in kinetic energy, or the change in potential energy. For stationary systems, for most systems, the change in kinetic energy and the change in potential energy for stationary systems it's minimal or negligible or doesn't exist. So for most cases, we can neglect the kinetic energy and the potential energy of a simple system. The piston's not moving fast enough, or there's no significant height difference. And in terms of the heat going into the system and the work coming out of the system and the change in the internal energy, those kinetic and potential energy values can be very, very small. So we could just neglect them. So the change in internal energy is really just the change in total energy of the system is mainly the change in internal energy of the system. Now, if we look at the other side of the equation, the energy coming in minus the energy going out, that can occur three different ways, as we've mentioned before, in an open system. It can occur in the form of heat coming in and going out, work coming in and going out, or mass flow of the working fluid coming in and going out. So we could have steam coming in, taking energy with it, or we could have water coming out at a lower temperature. We could have water coming out at a higher temperature, taking energy with it as well. And for closed stationary systems like this piston cylinder device, we're not dealing with mass flow coming in and going out. So we can neglect the mass flow element. So the only energy coming in and out of the system for a closed system is the heat going in minus the work going out, or vice versa. So what we can say is for stationary closed systems, the first law can be expressed as follows. The change in internal energy equals the heat applied to the system minus the work done on it. So let's say we heat up a system and the gas expands and there's work done by the system. If we want to account for the energy, we can say that the change in energy in here equals the heat applied to it minus the work done on it. And that's the simple first law expression for closed stationary thermodynamic systems. And we can apply that to a lot of simple closed systems, which we will do in a later chapter, and basically account for the energy. Where is the energy? Is it gone out in the form of work? Has it come in the form of heat? Is it still in the system? So the first law can also be applied to a thermodynamic cycle. So we know a thermodynamic cycle is a series of processes that ultimately bring the system back to its original position or original state again. So a simple two-process example would be a compression of a cylinder and then the expansion of a cylinder. So during the compression, we go from one state to another. If we get the work done during that process, and then if we go from state 2 back to state 1 again during the expansion, we can get the work done during that process. And if we take one away from the other, we get the net work in the middle. Now, the net work is ultimately the useful work that's being provided by the system. So if you think of the internal combustion engine of a car, when during the ignition, there is the piston, there's a power stroke, and the piston expands, and it does some work to the crankshaft to rotate it. However, on the return, the crankshaft is compressing the gas for the next cycle, and it's doing some work back into the system again. So what we need to know is that difference. We need the difference between the expansion and the compression, and that's the useful work that's going to drive the car. And from this graph, we can see that. We can do something similar on a TS diagram to quantify the amount of heat either added or taken away in a system. And then ultimately, if we apply the first law to a cycle, the change in energy of the system equals the energy in minus the energy out, which would ultimately be 0 to account for all the energy. So what we can say then is the energy in equals the energy out. So that means the net work out of the system equals the net heat into the system. Or in terms of power, the net power out of a system equals the net heat coming into the system. Heat rate, excuse me, Q dot heat rate coming in, heat transfer rate coming into the system. So that's the first law of thermodynamics applied to a thermodynamic cycle, accounting for the energy somewhere.